Welcome back to Calculus Universalis. Today we're learning how to approximate the area under a curve using Riemann sums, a method that AP exam creators love to test. So our graphs are going to look something like this, with a graph, and then underneath we're going to be able to use infinite and finite Riemann sums to approximate the area under the curve and therefore solve complex integrals without actually having to integrate. Let's go. This tool ultimately helps us to estimate a total value even when we don't know the exact antiderivative. So by the end, you'll know how to do left, right, and midpoint Riemann sums and how to tell if your estimate is too high or too low. Let's jump in. When we integrate a function over an interval, we're finding the area under the curve. Riemann sums estimate this by using rectangles. There are three main types. Left Riemann sum. Use the left endpoint. It's going to look something like this. Left endpoint of the rectangle. Right Riemann sums, where you're going to use the right end of the rectangle. And then midpoint Riemann sums, which are going to look something like this. So, to solve our midpoint Riemann sums, it's usually the most accurate. When we divide the interval into equal subintervals, each rectangle will have a width delta x, which is equal to b minus a over n. So our Riemann sum formula is going to be something like this. Riemann sum equals the sum of f of x times delta x. So it's basically just your height times your width. So let's start and practice on each kind. Starting off with the left Riemann sum. Let's go ahead and do it. Estimate 1 to 4 f of x dx using a left Riemann sum with 3 subintervals. Let's say f of x equals x squared. So it's going to be something like this. Interval 1 to 4 splits into 3 parts. Delta x equals 1. Let's make this a little better. 1, 2, 3, 4. So we'll have 3 rectangles underneath like this. So each of our thing is going to be a width of 1. And we just have to find the heights. In order to do this, we plug in each of our x values. Like that. And then solve. So then we get our heights to be 1 plus 4 plus 9 times our widths of 1, which equals 14. And that's our answer. Let's go ahead and solve a right Riemann sum. So if we have a table of f of x values from 0 to 6, let's use a midpoint Riemann sum with 3 subintervals. If x equals 0, 2, 4, 6, midpoints are x equals 1, 3, and 5. Let's say f of 1 is 10, f of 3 is 12, f of 5 is 9. f1 is 10, f3 equals 12, f5 equals 9. Midpoint Riemann sum. We're going to add these heights and divide and times by 2, which becomes 62. So we have 62 units squared using the midpoint method. Now our last example. let's overestimate or underestimate. Let's say f of x is increasing. Will the left Riemann sum over or underestimate? If f of x is increasing, it's going to look like this. The left is going to underestimate. What if it was decreasing? It's going to overestimate. And if it's midpoint, well, it's going to be pretty much neutral. That's why midpoint is more accurate. So, let's summarize what we learned today. Riemann sums are your first tool for estimating integrals. Left sums use left endpoints, right sums use right endpoints. Midpoint is usually more accurate. The estimate is too low if the function is increasing and you use left points. The AP often gives tables and asks you to calculate or input estimates. To practice on your own, you can estimate integrals, use table values, and see if things are increasing or decreasing over estimation. Next time, we're going to learn the trapezoidal rule and limits of Riemann sums.